Hello, these are the solutions to the remaining lecture review questions. So the question here is asking for what the net ionic reaction is for the complete neutralization of H3PO4 with KOH and water. So if we're thinking of this reaction here, H3PO4, the full molecular reaction would look like this. So I got my phosphoric acid plus my KOH. The complete neutralization means we're going to remove all three of the H plus ions with the hydroxide ion in the solution. That's an AQ, water soluble. And so that's going to form K3PO4, water soluble, all potassium salts are soluble, and then plus H2O to balance out. We're going to get three waters that form during the course of this reaction. So I need three KOHs to produce them. So three hydroxide minus ions reacting with the three H pluses off of phosphoric acid. So now when I think of writing my full ionic equation to try to get to the net ionic, I only dissociate my strong electrolyte. So I have a strong electrolyte KOH, but H3PO4 is not a strong acid, so it's just a weak electrolyte. So I leave this in the full ionic equation as phosphoric acid AQ plus 3K plus 3 hydroxide ion I could write AQ after those ions, but I'll save the time. 3K plus and a phosphate ion because K3PO4 is a strong electrolyte. Then I leave water intact because it's a non-electrolyte. So I only dissociate my strong electrolytes, so only dissociating the water-soluble ICs and the 7 strong acids. And so my spectator ion, if I was asked, would be potassium. It's the ion in identical forms on both sides of the reaction and can be canceled out. And so then everything else behind, H3PO4 plus 3OH minus, if you want to write the AQ in, plus phosphate goes the water, 3 of them still being formed. I lost the coefficient when I first wrote this reaction, but I got to carry that coefficient over. So that's the net ionic equation. Looks like D here. So that's our net ionic. K plus ion is the spectator. It's what we canceled out to write the net ionic. So it's the ion that's unchanged during the course of the reaction. All right, so let's take a look at this question here. So what's the oxidation number of chromium in CaCr2O7? So we know calcium's only charge in compounds is the +2 charge. Now oxygen, we know, has to be a -2 here. How do I know this? Well, I know that oxygen's usual oxidation number is -2, and there's 3 exceptions. The exceptions are compounds with fluorine. Obviously, this isn't a compound with F. Or oxides or superoxides. Now, an oxide or superoxide, these only form with things like alkali metals. So K can form KO2, that's potassium superoxide. It can form K2O2, that's potassium peroxide. And then it can form K2O, which is potassium oxide. So potassium oxide, the oxide ion, peroxide ion, superoxide ion. You might recognize them from nomenclature, but the difference in these is our oxidation number of O varies from -2 to -1 to -0.5 in those compounds. But you'll pick up those oxidation numbers because they only form in cases where you know the charge of the metal. So anyways, just putting aside that clearly this isn't an oxide or superoxide. So that's how I know this oxygen charge has to be -2. There's 7 atoms. That makes the total collection of oxidation numbers from the 7 O's -14, +2 for the calcium. All of these have to sum to neutral because this molecule here is uncharged. There's no charge indicated in the formula, so it has to be an uncharged molecule. And so that means the total oxidation numbers from the 2 chromiums has to be 12. And there's 2 chromiums, so each one is +6. So this is the math below showing how the cancellation works and the summing up to the oxidation numbers go to 0 for the whole molecule, and the per atom up top. So per atom oxidation number for chromium is +6. Which statement is true about the reaction below here? So we have ClO2, water going to HClO3 and HCl. And so let's start assigning oxidation numbers. Oxygen has to be -2. I know hydrogen by rules of +1 and a -2. I'm going to assign all the ones I know by rule. I know H in molecular compounds is +1, O in non-F or peroxide superoxide compounds is -2, H in molecular compounds is plus. That makes chlorine here its usual rule of minus. And so then I can determine all the other atoms by just doing the math. So -4, so +4, so +4 for chlorine. And then this chlorine in HClO3, -6, +1, so that's a +5. And then that's every atom on all of the molecules in this reaction. And so the hydrogen actually has nothing going on here. The H is +1, +1, +1. So the H is unchanged. If you look at the oxygen is unchanged as well. We have -2 O's on both sides of the reaction, so the O doesn't have anything going on. And then chlorine is actually undergoing both the oxidation and the reduction here. So chlorine is going to the +5 state, and then chlorine is, some of them are going to the -1 state. So 5 of them go to the +5, and then one of the 6, so you have 6 chlorines in the reaction, one of them goes to the minus. And so we have 5 of the 6 chlorines that are losing 1 electron, and then one of the 6 chlorines gains 5 electrons to go to the minus state. And so we have 5 chlorine atoms lose 1 electron, 1 chlorine atom gains the 5 electrons. We actually have chlorine being both oxidized and reduced in this reaction. And then the key, though, is that the H and the O are unchanged. There's no difference in the H and the O. It's only the chlorine that's going from a +4 to a +5 and a -1. So that's chlorine gaining electrons to go to the minus and losing electrons to go to the plus. And so interesting reaction, but a case here where the same atom is undergoing the oxidation and reduction. Which metals will dissolve in a solution of H plus ion? So the key here is really that HNO3 is really H plus NO3 minus. And so that's right here in terms of the case. So I can take all the metals up here, and each of these metals here will dissolve in H plus solution. And so lead is above hydrogen, so lead forms lead-2 plus ion. This is why actually lead is so bad in plumbing, because if you have corrosive water that's of relatively low pH or high acidity, then it's going to leach out lead ions into the water. That's going to be pretty bad. So zinc can do this too, because zinc is above hydrogen on the chart. So B and C can do this, but not mercury, because mercury is below H plus on the chart. So mercury could dissolve into a solution of these 2 ions, but not the ions above it. And so metals will react with the charge state below them. So you could take like lithium, potassium, barium, and you can put like picture, let me draw the red box. Let's consider these 3. They will dissolve into the cation solutions that are below them. So they'll dissolve in solutions of calcium ion or sodium ion, etc. So the activity series is telling you that the metals at the top of the chart are more reactive than the elements at the bottom of the chart. So the metal solids, the neutral metals at the top of the chart, will dissolve in the cation oxidized solutions that are below them. So that if you picture, for example, like can we write the reaction for nitric acid and say zinc? I think we can. So zinc solid, so neutral zinc, should react with the HNO3 solution, aqueous, and the product should be H2 gas, which floats away, and then forming zinc 2 plus, pairing up with nitrate to the minus, so 2 nitrate ions, and then we'll need 2 HNO3s to put us into balance. So we're making H2 gas, which should float away from the reaction, and then zinc nitrate. If you think of doing this reaction with mercury, there'd be no reaction would take place. If you then think for a different case, let's imagine barium solid. If you put barium into a solution of, say, let's say, it doesn't really matter what's below it. Let's say iron 2 plus. then the iron 2 plus aqueous, the iron will absorb the electrons off barium, so that barium forms barium 2 plus aqueous, and then iron solid forming. And the key is really looking at these two activities of the solids, of the neutral atoms, and you need to start with a more reactive metal and produce a less reactive metal, or a more reactive neutral substance and produce a less active neutral substance. And if you think of zinc, zinc is higher in activity than hydrogen. Hydrogen being the one non-metallic element on the chart. So you just want to be higher than the cation that you're reacting with the solid in order for a reaction to take place for these redox reactions. So that's a couple examples here using the activity series. So another net ionic equation question. So what is the balanced net ionic equation for when iron sulfate and KOH are mixed? So iron sulfate here, water soluble, according to the solubility chart. So Fe2SO43 plus KOH should form the insoluble iron hydroxide. How do I know this is iron 3 solid? And how do I know it's insoluble? Insoluble comes in the solubility chart. And then I know my charges here are 3 plus and 2 minus in Fe2SO43 because I know sulfate's a 2 minus. I know sulfate's a 3 plus. And so I keep my charge states the same. We're not changing the charge states of the metals in a metathesis exchange reaction. My other product here should be K2SO4, which is water soluble, AQ. And so KOH is an AQ as well. And so for the net ionic equation should be KOH is really K plus and OH minus. Iron sulfate is its ions. K2SO4 is its ions. So your spectator ions are going to be K plus and sulfate. I'm not going to show this out, but your net ionic should be iron plus hydroxide ion forming FeOH3. So it should be this reaction here. Let's get into some solution formation. So we add 0.15 moles of lithium chloride to a 250 milliliter flask. We then fill with water, assuming the solid dissolves, and we take by pipette 4 milliliters of the solution and then change it to, a total volume of 50 milliliters by filling it with water to the mark. So we're making solution 1, calculating its concentration. So we're putting, for our concentration of lithium chloride in our first solution, let's call that, I'm going to call this Roman numeral 1. So this is the first solution that we're preparing. It'll be equal to the 0.15 moles that we put into the container, and then we're filling it to 250 milliliters. So I'm putting that into liters to go to m moles per liter. And so I think that's 0.6 m, just being silly to make sure I don't screw the math up. Yep, 0.60 big M, and that's just moles per liter. So you can call it 0.6 m or mole per liter. So then we take 4 milliliters of this solution, and then we're going to change its concentration and try to calculate the new concentration. So we're going to take 4 milliliters of the solution, put it into a new flask, and add with water. So we're doing a dilution. And so we want to do this dilution step. Now there's two approaches. We can take M1V1 equals M2V2, or sometimes I call it MIVI equals MFVF. And so we're trying to find the final molarity by taking the M1V1 over V2. And so this is my M1. This is my V1, and then my V2 is just 50 milliliters. And so if I solve that math there, so 0.6 times 4 divided by 50 is 0.048 molar, so that would be answer B. Now that's good, so that if you take and solve for M2 by going 0.60 molar times 4.0 milliliters divided by 50.0 milliliters, then that works out to be answer in B. So 0.048 molar. Now I didn't need to convert to liters here because, our milliliters cancels into milliliters. But now an alternate approach would have been just to say, well, how many moles are there here? You know, if I take 4 milliliters, so the number of moles of lithium chloride that are in the 0.60 mole per liter solution, where I take 0.0040 liters, that corresponds to 0.6 times 0.004, that's 0.0024 moles of lithium chloride, and then we're just putting that into a new solution where the total volume ends up being 0.050 liters. So divide that by 0.05, we get the same result here for answer B. So two kind of thoughts. Either A, use the dilution equation, but just know that this works for dilutions, and that's specifically the type of problem that equation is derived to try to understand, or just go back to the concept of molarity, that molarity is moles over volume. And we symbolize moles as M, volume as V, so that's N over V when we write this. So M is N over V. Last page, what is the molar concentration of chloride ions in 2.0 M FeCl2? And so the only big thought here going on is that this solution involves a ionic compound that's water soluble, so therefore it's really iron 2 plus and 2 chloride ions. And so the concentration of chloride, that's the brackets just mean the molarity of what's inside. So the molarity of the chloride ion would be the moles of chloride per unit volume, but we're starting from 2.0 moles of FeCl2 per liter, and there's every 1 mole of FeCl2 that dissolves in solution, we get 2 moles of chloride ion. So we're just doubling that concentration. So it should be 4.0 molar. And then write the balanced equation for aluminum and nitric acid. How much nitric acid in liters is needed to react with 27 grams of aluminum? Okay, so the reaction should look like this. Should look like aluminum solid reacting with HNO3 aqueous. The product should be H2 gas and then aluminum nitrate. Al3 plus, so aluminum going to the 3 plus, so aluminum is oxidized, and then the hydrogen goes from plus to 0. Hydrogen's gaining electrons, so therefore is reduced in the reaction. And so then to balance this out, 3 HNO2s, that's going to be a fraction of H2s, so that would be 3 halves H2, so let's double that to 3, that gives us 6, so that makes that 6 to get 6 H's on both sides. So I have 3 H2 gas. Let me make sure that that's clear. And then, so 6 hydrogens on both sides, so we are going to need 2 AlNO3s, put 6 nitrates on both sides, and then 2 aluminum. Okay, so we can write and balance that reaction here. So then if you have 27 grams of aluminum, that happens to correspond to about a mole, because the molar mass of aluminum is about the same quantity, 27.0 grams per mole. And so if I'm going to work out the number of milliliters of the HNO3 solution that we need to react with and neutralize the 27 grams of aluminum, well, let's just use the molar mass of aluminum. For every 2 moles of aluminum, we need to add 6 moles of HNO3. And then we're delivering HCl with a concentration of 0.500 moles of HNO3 per liter of solution, except this is backwards. This is a good example of what I was talking in class of. If we show our work, we'll hopefully catch a mistake. I want to divide by the molarity, because it's 0.500 moles of HNO3 canceling per liter of solution, and a liter of solution is 1,000 milliliters. Okay, so we're going mass of aluminum to moles of aluminum to moles of HNO3, moles of HNO3 to volume of the solution, volume into milliliters. Oh, sorry, we actually didn't need to do the volume to milliliter conversion. The answer was actually just looking for the solution directly in liters. So no need to convert to milliliters here. In fact, I don't know why I thought we were looking for the volume in milliliters, looking for the volume in liters. So the question says how much HNO3 in liters. So let's make sure we know what we're looking for. So 27 divided by 27, so about 1 mole of aluminum. So then times 6 divided by 2, and then divide by half a mole means we need to add 6 liters of the HNO3 solution in order to deliver 3 moles of HNO3 in order to react with the approximate 1 mole of aluminum we have present. Okay, so that wraps up this review packet. I can redo problems on Monday if anybody wants to see anything again, or if you want to discuss any of these in our lecture review before the start of class, let me know. You can also bring other questions to the review, and I'll try to hopefully get through those problems on Monday. So exam next Tuesday. So thanks for watching if you watch this, and have a great weekend.